Some time ago, I came across this YouTube video by Matt Vermeeren about the way that rainbows actually work. I think it's an excellent video because it goes through all the different perspectives of a rainbow and the way that different wavelengths of light reflect through a droplet. And at the end, it uses derivatives to explain the real cause of colors in a rainbow. This video is linked in the top right corner right now, and you should definitely go watch it before continuing on with my video. And that's because in my video, I'm only going to be discussing this single mathematical problem about the way that light refracts through a droplet of water.
Let's look at what happens within a single raindrop. The sunlight, coming in from the left in this diagram, is broken or refracted as it enters the raindrop. Then it is reflected on the inside of the raindrop and finally refracted again when leaving it. The breaking of light is related to the fact that it moves more slowly in water than it does in air. The angle of refraction can be expressed using a formula called Snell's law. If you know some trigonometry, it's actually a good exercise to calculate these angles. We won't need exact formulas for this explanation to make sense, but if you manage to do this exercise, you'll notice that the angle of the outbound ray depends on how far from the center the inbound ray hits the raindrop. The angle, which is called alpha here, depends on the distance d from the center.
Since the video didn't go through the specific trigonometry in this problem, I decided to challenge myself, and so I solved the problem and made a desmos file visualizing the entire path of the light. You can see here that we start with a circular drop of water of radius 1, and we have a light ray entering from the left whose height can be adjusted by the slider, and it can be both positive and negative. This light ray impacts the water droplet at a specific point on the boundary, and afterwards it is refracted according to Snell's law. This blue line is just a construction line, and you can see this black line is the path that the light will go. Afterwards, one big assumption that this model makes is that the light will reflect over here instead of refract through. This won't always happen, but it happens often enough for rainbows to be formed. And so I made another construction line and marked the point at which this line impacts the boundary. And now, using the law of reflection, I can determine the path of the third ray of light, which ends up over here on this side of the circle. And once again, all of these blue lines are just construction lines, so you can completely ignore them. Lastly, the ray of light refracts one more time and exits the droplet of water at a certain angle. Keep in mind that throughout this entire process, I've made the equations so that as I change the angle, everything else also changes to match the path that the ray of light actually would take. Let me just quickly and very vaguely go through the process I took to calculate this output angle here, given the input distance. Because the x-axis and the incoming ray are parallel, this angle and this angle are equal. I'll call that A. Angle A can be easily calculated using the inverse sine, and so now you know this angle, and you can use the law of refraction to calculate this angle. Since these two blue lines are radii of the circle, this angle equals that angle, and because of the law of reflection, this angle equals this angle. This then means that all four of these angles are equal, and you can also use that to calculate these two angles. Refraction happens once more down here, and because you know this angle, you can calculate this angle. Lastly, since the output we need is this angle, which is equal to this angle, we need to calculate the angles inside this triangle. We already know the size of this angle, and now the target is to get this angle over here. It took me a long time to think about how to actually find the size of this angle. The way I eventually found it is by noticing that this angle over here from the negative x-axis all the way around to this blue line is equal to the angle from this blue line all the way around to this blue line. We know all three of these angles, so we can find the size of this overall angle. That angle is equal to this angle, and knowing this, we can find this over here, and knowing this, we can find this. And so now we know this angle, we know this angle, we can therefore find this angle, and the final output angle. So after you go through that entire process and simplify the expression, you end up with this equation for the angle of the outcoming ray, given the height of the incoming ray. You can see that the angle is expressed in terms of the refractive index of the outside and the inside. And I just searched up the refractive index for air, which is basically 1, and the refractive index for water, which is roughly 1.33. These can also be changed, and you can see that the path of the light changes depending on the refractive index. Lastly, I can turn off the entire diagram and show you the shape of this equation. It's scaled up by a factor of 100, so after zooming out and looking at the positive side of this curve, you can see it almost perfectly matches the curve shown in the video. This is all I have in this video. If you want to find a link to this desmos file, have a look in the description of this video. Other than that, thank you for watching.